Section 17.6, longitudinal standing waves. So first we could imagine a longitudinal standing wave pattern on a slinky. So the slinky is sliding forward and back. And what we'd find if we got the oscillation just right is that there'd be points that are moving quite a bit back and forth. And then there are other points at the nodes where there's no motion. Where you could put a piece of paper there and the slinky wouldn't be moving against it. And yet on either side, the slinky would be moving a lot. So this is pretty wild in the longitudinal direction. And one of the reasons we care about longitudinal standing waves is because sound, remember, is a longitudinal wave. So we can get this resonance, this standing wave, if we have the conditions just right. So one way we can do this is if we have an open cylinder, a tube that's open on both ends, and if we have a frequency like a tuning fork nearby, right, that's at just the right frequency for this length, then the oscillations or disturbances from the tuning fork can actually create a wave inside this tube. And it can be a standing wave if you get it just right so that when it reflects off the end, it all matches up for this constructive interference. What we'll find is that open tubes, when it's open on both ends, there needs to be an antinode at that end because the air is free to move back and forth. And there will need to be at least one node in the middle. So antinode, node, antinode, that's going to be our fundamental frequency. And we could look at this and note that it is about half of a wavelength, right? Half of a cycle is the entire length. For the next one, the next harmonic, we'd still need antinodes at either end, but we can add another antinode in the middle. The advantage of this is that now, notice we go down and up if we just follow one edge of this. We now have a complete cycle. The entire length is equal to one wavelength. Now, if we use this relationship along with our speed relationship, that V equals frequency times the wavelength, right? And we want to solve for frequency to get frequencies out. So frequency is equal to V divided by the wavelength. And what I'm going to do is solve these for the wavelength. Wavelength is equal to L, wavelength is equal to 2L. So it turns out we can write it like this as the general result, that the frequency of every harmonic is equal to N, the number of the harmonic, times the speed of sound, divided by 2, divided by the length. So this is for a tube that is open at both ends. We can thus calculate its frequencies from the first harmonic, second harmonic, third harmonic, fourth harmonic, and so on and so forth. And it comes from this pattern, that's what always is building up for it. One thing to note is this equation looks identical to the standing wave on the string. And that's because we have this symmetry where the standing wave on the string needed nodes at both ends. This one just needs antinodes at both ends. A key difference here, though, is that the V here is not the speed on a string. It's now going to be the speed of sound, which is often 343 meters per second. All right, so armed with that knowledge, let's see where we might see an open tube like this. Well, one example, it turns out, is playing a flute. So when all the holes are closed on one type of flute, the lowest note it can sound is the middle C, 261.6 hertz. If the speed of sound is 343 meters per second, and the flute is assumed to be a cylinder that open at both ends, determine that distance L. So here we have the flute is one example of this open tube. We can use that equation. The key thing with that last equation is we need to determine the N value, right? They've given us the frequency, so that part's good. They even gave us the speed of sound, which is also good because it is technically temperature dependent. But in most cases, we'll just use 343 meters per second. So what about N? The key is that This is the lowest note. The lowest note is going to be the fundamental, or the first harmonic. So that tells us that n must be equal to 1. So that's some key information that's tucked away in the problem for you to uncover. Once we have that, the problem is now very straightforward. Right? We can look up our equation for a tube that is open at both ends, and we'll rearrange it to solve for L. So the way I like to think about that is I'll multiply the L up here, right? And multiply both sides by L so that L cancels, and then divide by the frequency. And so that's exactly what they did. It's like the L and the frequency just traded places. So if we plug in n equals 1 times the speed of sound, divide by 261.6 hertz, we find that the length is 0.656 meters, about half a meter, which is about what a flute looks like. So that's very reasonable. Some other examples of open tubes are often organs are this way. Yeah, and we'll see there's another type of tube that sometimes pops up. So the other type of tube we might have is if one end is open and the other end is closed. I like to call this an open-closed tube. This, it turns out, is most like a clarinet, that a clarinet is closed at one end and open at the other. And the key difference here is that at the open end, we're still going to have an antinode, but at the closed end, the air is not free to move around that much. So it's now a node. There's no motion there. That means we only have a quarter of a wavelength here. And when we add another node in the middle, we don't yet have a full wavelength. We have 3/4 of a wavelength within that length. Versus this is a quarter of a wavelength equals L. Oops, it should be a 4. So if we put it all together along with our speed of sound, we'd find that if the tube is open at only one end, closed at the other, the frequency is given by this similar but different equation. N times the speed of sound, divided by 4, divided by L. This is the only one that has a 4. And also, the harmonics are different. So the even harmonics get skipped. There's no resonance there that's possible. So N can be 1, 3, or 5 for these open-closed tubes. So that's an important distinction there. That's where you'll want to keep these equations straight on your note sheet. So make sure to do that, to have some good notation there. One last thing is complex sound waves. So it turns out if you hear a sound wave, it's not usually that simple sine wave. Turns out it's kind of a weird bumpy pattern, but that bumpy pattern can be deconstructed into a combination of individual sine waves, right? And it's just a different amplitude of each, right? So there's one that has a really large amplitude, and then these higher frequencies that have a smaller amplitude and create this interesting pattern. And this is what gives every sound its own unique timbre. That's a fancy music term, but it's what makes a trumpet sound like a trumpet, or a singer sound a particular way, or a guitar string, right, sound some other way. Is it's the relative amount of each of the harmonics combined. So if you can adjust the amount of harmonics of something, then you're able to adjust the color of how something sounds. And so that's where a spectrum analyzer is really useful. And really complicated patterns, turns out, are just these combinations of different frequencies and or different harmonics. And even if you're just sounding a single note, there's a whole bunch of other harmonics built in there. Little did you know. So this brings us to the end of chapter 17. Lots of cool things with interference of waves, especially dealing with sound and how sound can interfere. So do stick around. I'll include a couple more demos as well. So I encourage you to see those, to see some of these cool effects in action. All right, thanks y'all. That is the official end of chapter 17.